Good morning. So this will be the last lecture on Bessel functions chapter. So this is basically just a hint, well, not just a hint, we'll say more on that. But among other things, this is a hint on problem 95.4, which is on the homework. So some of it will be left for you to finish the problem. But I want to point out how the method of variation of parameters, which we learned as one way to deal with non-homogeneous equations, can be used no matter what type of eigenfunctions you deal with or what type of series you deal with. So this is actually a good opportunity to review the method and again focus on the main idea of the method and see how this adapts when you have to deal with Fourier-Bessel series. Because the idea overall is the same. So let me just state it roughly speaking. There are two, it's always useful, by the way, to go over a big overview of the algorithm, like big steps, and then make the details of what each step means in your case. So you have a non-homogeneous problem, you look at the homogeneous part of it. So you drop temporarily the non-homogeneous term, and you look at how the solution would look like if you were to solve the problem, if you were to solve the homogeneous part of the equation. So once you identify the series format for that solution, that means in the variation of parameters, you will look for a solution of the same problem, of the non-homogeneous problem, in the form of the same type of series, meaning a series with the same type of eigenfunctions, but with coefficients left as functions of t yet to be determined. So that's what it means, variation of parameters. So the parameters that you would know what they are in the homogeneous part of the equation, now you leave them as unknown functions and you obtain differential equations for each of those coefficients. And that completes the problem, the solution of the problem. So that's the overall view of the method. Now let's see how this plays out in our case. But before we do that, let's review briefly a couple of formulas. Take a look at the formula sheet. We're going to need in this problem the Fourier-Bessel series with Newman conditions. So in that case, remember the eigenvalues, one of the eigenvalues is 0, just like in the case of cosine series. And the other of them are roots of the Bessel equation. So the positive roots of the same Bessel function. So a function can be written in terms of this series where alpha j are the roots, the positive roots of j naught prime of alpha c equals 0, or remember equivalently, because of the relation between j naught and j1 of alpha c equals 0. So these two are equivalent, right? Because j naught prime is minus j1. And c is from the domain, right? So the domain for x is 0 and c. In the problem, c will be 1, but this is the formula. And remember the formula for these coefficients, a1 is given separately because it's a different integral. So from 0 to c x of x, f of x dx. And the rest of them from 2 to infinity, it's given by this integral, c squared over j naught alpha j c quantity squared, and the integral from 0 to c x f of x j naught alpha j x dx. Also, to save some time, and we're going to need it in this problem, in some previous lecture, you can take a look if you want to see the details. We show that with these conditions, the Bessel series for x squared is c squared over 2, so that will be a1, plus summation from 2 to infinity 4 over alpha j squared j naught c alpha j times j naught alpha jx. So we're going to need this also. All right, so the problem 95.4, it's a modified heat equation to make it non-homogeneous, right? So you have u partial t on the left-hand side, u partial rho twice 1 over rho u partial rho. And what's new here, it's a constant term added to the problem called q naught. This is called a specific heat. I I think. Actually, I'm not sure about it, but let me see actually if it's not specific heat. But anyway, the meaning of it is that this is basically let's call it internal heat. So meaning that, because I think there's a different definition for the specific heat from a physical perspective. But anyway, basically what you have to imagine is that in addition to the heat that flows across the radius, the object, due to, for example, some chemical properties, generates a constant heat per unit of time that is added to the overall heat energy on the right-hand side. So that's additional heat term, basically, which makes the problem non-homogeneous. Think of it as a constant, a positive constant. It doesn't have to be constant, a positive, but anyway, it's a constant. And a non-zero constant, because otherwise it would be homogeneous. And the boundary conditions state that on the surface, so the radius is 1 in this case, and the exterior of the cylinder is insulated. So that means partial rho at 1T is equal to 0. And the initial temperature U of rho 0 is given by the function A rho squared. A is a constant, and rho squared, that's why I actually needed x squared, because I'll need this series a little bit later in the problem. So let's go over how we deal with, like I said, with the homogeneous part of the equation. So we identify the type of eigenfunctions that we deal with. So again, when we proceed with the variation of parameters, the first part is to look at the homogeneous part of the equation. You don't actually solve it completely. You just basically have to go through the process of looking at the homogeneous part until you figure out the eigenfunctions and how the series looks like for the solution of the homogeneous part. So the homogeneous part obviously should be familiar to you already. So if we drop Q naught temporarily, and remember how it goes from here, we take a product form for the solution, and we're going to skip some intermediate steps because we know already where this goes, right? I mean, the Sturm-Liouville problem, the equation in R ends up being rho R double prime plus R prime plus rho alpha squared R equals 0. Alpha squared was the separation constant, so on and so forth. You know the drill. With the boundary conditions R prime of 1 equals 0, which comes from this condition over here. I'm going to need later also this same equation with rho attached to R prime, because remember, we multiply by rho to avoid the fractions, but remember this comes from R double prime plus 1 over rho R prime plus alpha squared R equals 0. We're going to need that later, and we'll see why that's the case, but this is essentially the same as this. All right, so the eigenvalues, the way you denote them according to the formula will be, of course, this one has 0 eigenvalues as well, so alpha 1 will be 0, and then the rest of them, alpha j, are the roots of, pay attention here, j naught prime of alpha equals 0, because c is equal to 1 in the case of my problem. Or again, equivalently, j1 of alpha equals 0. So from 2 to infinity, all the other roots, or the other positive roots, will be the solution of this, this equation. And another crucial thing that I want you to keep in mind, because J naught of alpha rho solves the equation, so J naught of alpha rho, remember, solves the Sturm-Liouville problem. That means if I plug in J naught of alpha rho into this equation, it should be equal to 0. Okay, so this will be needed later, as you'll see immediately. So if I plug in J naught of alpha rho into the equation, I'm going to have J naught of alpha rho double prime plus 1 over rho J naught of alpha rho prime plus alpha squared J naught of alpha rho. This is simply stating that we know that J naught of alpha rho solves the Bessel equation of order 0, which is the Sturmoville problem in this case. So I want you to keep this in mind when we move on to the next step. So now we know basically how the homogeneous solution looks like. If we solve, and this is the part when you don't have to solve it, right? I mean, because remember, our goal is to solve the non-homogeneous equation. But if we are to solve the homogeneous part of the equation, we know that the solution, well, we will solve, of course, the equation in T for every alpha j. And eventually the solution, of the homogeneous part is going to be in the following form. Some constant a1 times t1, right? The equation, the solution for the corresponding equation in t, and then a summation from 2 to infinity involving the rest of the Bessel functions, some coefficient aj, some solution tj of little t, right? So, and then the Bessel functions coming from the Sturmoville problem, so j naught of alpha j rho. I should say here t1 of t to make it clear, right? So for each eigenvalue, you solve the corresponding value of t. So pause for a moment and make sure you understand that this is what you end up with if you were to solve the homogeneous part. In fact, you can take a look at previous example we've done in this chapter, and you'll notice that indeed we got these solutions, and these tj's are in terms of exponentials, whatever is the solution for the equation in t. But remember, you don't need to go that far at this point, because your goal, of course, is to solve the non-homogeneous equation. So here is the moment when the variation of parameter kicks in. So according to the variation of parameter method, you're going to look for a solution of the original problem in the form of the same series, but with coefficients in t yet to be determined. So you look for the solution of the original problem in the form u of rho t equals some unknown function of t. So this whole thing becomes some unknown function of t, which is yet to be determined. And then the summation of some unknown function, I'm going to use the same letter aj of t, times the Bessel function j naught of alpha j rho. All right, so this is basically the main idea. We're going to make a second part to finish the problem, the hint I want to provide, basically. But remember, the goal again is to choose a solution for the non-homogeneous problem over here in the form of a series involving the same eigenfunctions as for the homogeneous one, with the coefficients given by functions in t to be determined. That's the main idea. Okay, identify the eigenfunctions of the homogeneous part, take a series solution using the same eigenfunctions but with coefficients now not given by constants but by functions of t. Okay, so let's end this part here, and we're going to continue with the second part in a moment.